everyone. This webinar is about benchmarking Half Precision RISC-V multicore processor using Cloud5. So let's get started. The agenda of webinar is such that first of all, there will be an introduction of host and company. After that, there will be a guest presentation. The guest right now with us is Quesada Pablo from University of Santiago de Compostela, and he will be presenting his work, his upcoming work about what he is going to do on RISC-V processor using Cloud5 and what he has done so far. After that, I will be presenting how Cloud5 is helping the guest. And after that, I will be telling you how Cloud5 is helping the RISC-V community in general and open source community. After that, we will get to the contact info and you will be able to post questions in the comment. So a little introduction about Cloud5 team. I am Ali Tariq. I work as solutions engineer at 10xEngineers. I have background in design of digital systems, embedded systems, and a little bit in design verification. Currently, I am focused on DevOps and Linux system administration, and I am working as technical staff member on Cloud5 project. The other member who is working on Cloud5 is Mohammad Moiz Hussain. He is working as product lead. He has background in embedded system application development, Linux administration, and SOC design verification. He is currently focused on Cloud5 as project lead and monitoring its various aspects. As Cloud5 is an R&D project of 10xEngineers, so a little introduction about 10xEngineers too. 10xEngineers is primarily design and verification services company, and it is focused exclusively on RISC-V and image signal processors. It has various clients in design and verification, in physical design and comparison toolchains and AI on the edge, and it is still thriving in various fields. So now I'm going to explain what is Cloud5 and the vision of Cloud5. Cloud5 is actually a platform for testing RISC-V applications on RISC-V instances. It can or cannot be cloud-based, and it can also be self-hosted depending on the need of the user. The tooling and features are available out of the box. So that means users do not have to install anything on their machine. They just have to log in and all the tools will be available on the platform. Lastly, if you have a GitHub or GitLab repository and you need to use RISC-V CI, the CI will be running on RISC-V hardware or emulated instances, depending on the user need. We also have other services like sandboxing and firmware development. For more information, you will have to visit our services page. So now we are going to get to the guest presentation, and Pablo will be presenting what he has done so far. So over to you, Pablo.
Okay, thank you. Okay, you see the presentation, right?
Yes, we see that.
Okay. So, well, hello, everybody, and thank you for coming and listening this webinar on 60 bits for remote sensing hyperspectral image processing for onboard satellite on RISC-V and ARP architectures. My name is Pablo Quesada, and I am associate professor at the University of Santiago de Compostela, that is located in Galicia, northwest of Spain. This university has two campuses, one in Lugo City and another in Santiago de Compostela, and has more than 24,000 students enrolled in more than 200 undergraduates and master degrees, as well as PhD programs. And we are approximately 4,500 professionals among teachers, research members, and administration staff. Well, I'm in the Department of Electronics and Computing, and I teach in the Computer Science degree and the Artificial Intelligence degree, as well as coordinating the Master degree in High Performance Computing in this university. And I'm also the research collaborating in the Centro Singular de Investigación en Tecnologías Inteligentes and member of the Remote Sensing Hyperspectral Research Group on this university. So, remote sensing image processing has increased in recent years, mainly due to increase in the number of satellites, unmanned flights, and drones, which incorporate different types of sensors to capture information from the Earth's surface. Open access to databases that store information acquired by satellites has also led to interest on the part of government organizations, companies, and research groups. Images used in remote sensing have a wide range of applications, from environmental monitoring, security and surveillance, mineral exploration, or monitoring and quality control in agriculture. One type of sensor used in remote sensing is one that acquires multiple spectral bands, usually in the visible spectrum and some bands of the infrared spectrum, called multispectral sensors. And if the number of spectral bands is high, they are known as hyperspectral sensors. In addition to spectral resolution, the sensor also improves spatial resolution, reaching an accuracy of 3 meters, for example, as well as temporal resolution, acquiring data from the same area in less time, leading to very high resolution images that in hyperspectral field requiring efficient processing, not only at the level of the information they contain, for example, a high percentage of accuracy in the classification of the Earth's surface, but also that they are efficient in the use of hardware resources at runtime. One approach to achieve the latter is to implement well-known algorithms for hyperspectral remote sensing data analysis, for example, supervised classifiers, in parallel architecture to reduce execution time. Another alternative is to design new scheme for the analysis of these images based on algorithms that we know that are scalable when running on architecture with many cores, such as multicore processors and GPUs. In the case of spectral imaging, the high number of spectral bands made it necessary to adapt the algorithms following a spectral or spatial processing patterns. We can also reduce runtime and optimize hardware resource by reducing the number of bits used in arithmetic operation, for example, by using the standard 16-bit format, also named binary 16, the 16-bit Google Brain floating point alternative, the proposal of NVIDIA using 19-bit TensorFloat, for example, or even reduce it to 8-bit format for floating point operation. You probably know this is, for example, the approach for large language model training in artificial intelligence. Reducing the volume of data, for example, with compression algorithms that allow further analysis even with the data compressed, or reducing the number of spectral bands is also leads to a reduction in execution time and storage requirement. Thus, we also reduce the space required to store data in memory and speed up analysis by having to process a smaller amount of data. This is known that feature extraction is a very common stage in many remote sensing data analysis pipeline. Spectral reduction from feature extraction or feature selection seeks to retain the similar amount of information to the original images, but with fewer bands. Evaluating the performance on this type of algorithms is of great interest regardless of the type of application. Even more if the objective is to process data in real time for decision-making on board satellites. The architecture for onboard processing in satellites and space mission can be mainly divided into field programmable gate arrays, digital signal processors, microprocessors, and recently into adaptive compute acceleration platform with different features and applications. A common feature of all this hardware is radiation fault tolerance. FPGAs have the advantage of being immune to radiation with high performance per watt, while processors have limited computing power due to the degree of integration to achieve some tolerance to radiation. But compared to a FPGA, they are more versatile and have a faster software evolution, leading to a larger development community. The adaptive compute accelerator are new heterogeneous systems with a high degree of integration that incorporate a specific hardware for artificial intelligence, inference, digital signal processor, reconfigurable FPGAs, and multicore processors. That is all-in-one solution. In the context of efficient multicore processing, the high-performance spacecraft computing project of the National Aeronautics and Space Administration, NASA, began by developing multicore processor based on ARM architecture with high radiation tolerance to improve onboard computing capability for future space missions. In 2022, NASA adopted RISC-V as a reference ecosystem in this mission. In this trend, the European Space Agency has been and is working on its own processor based on Spark, and recently also on RISC-V. planning to put a 60-bit processor with 16 cores into orbit next year. So the need for versatile onboard computing is driving the development of multiprocessors for space mission, creating heterogeneous and more integrated systems to respond to a wider range of applications. Looking at the development trends, in this architecture toward heterogeneous system with ability to solve different types of problems, it is necessary to have a comprehensive set of tests that allow evaluate the performance of algorithms used in remote sensing. This research project aims to study the performance of techniques for the extraction of features from hyperspectral images in architecture designed specifically for a space mission focuses on heterogeneous architecture with multicore processors. The algorithms to be evaluated in this research project will be representative in the pre-processing of remote sensing images, thus creating a benchmark suite on 16 bits regardless of the time of application. The result of the study will provide valuable information to continue the analysis in other stages of a classic remote sensing pipeline, for example, compression, classification, or the registration of hyperspectral images. 16-bit implementation of a representative set of algorithms is the first stage of a classic hyperspectral image processing pipeline in this project. We plan to implement, among other, principal component analysis, wireless transfer in one-dimensional space, superpixel-based segmentation, and some mathematical morphology operation. This development can be carried out in personal and commercial of the shared ARM or RISC-V architecture, considering the limitation, for example, that could be found in equivalent system for onboard processing. For example, let's say lack of optimization at the hardware level, such as streaming, simple extraction, multiple data extension, advanced vector extension, or operating system support for multi-threading. The second goal is evaluating the performance at the application level, comparing the result with 32 and 16 bits, and the performance at hardware level in terms of execution time and resource use. This analysis can lead to the creation of a hyperspectral imaging test suite representative of current and future sensors to test the 16-bit implementation. There are currently several public repositories with hyperspectral images that can be accessed through an API, which simplifies integration into projects and simplifies access to such information, both for the creation of an initial dataset and for further updates. So the work is being organized into directories by each algorithm with different implementation based on the architecture. We also have a base x64 version for Intel and AMD, as well as a CUDA implementation. And we have been able to speed up the development side thanks to Cloud5 services with continuous integration built through GitHub pull requests and with access to RISC-V hardware such as the Star5's Vision 5.2 board, for example, as well as the QEMU software and compute instances with cross-compiler. So in addition to these cloud services, we have in our research group an NVIDIA Jigsaw development kit with an ARM CPU and an NVIDIA Ampere GPU, so we can cover all this type of architecture. We are now with the test of a base algorithm in 16 bits in the different architecture, so we can replicate the same structure for each new algorithm we plan to add to our benchmark. Well, this is just a snapshot of the bibliography that I invite you to read if you want to learn more on remote sensing, hardware for space mission, or the RISC-V architecture. So just for ending this presentation, let me thanks to Cloud5 for providing access to RISC-V instances and all the team for the support on the initial setup, with a special thanks to Ali for the outstanding help in a lot of small details, that will make much longer to figure it out working alone for sure. So that's all for my side. Thank you for attending and thank you for listening.
Thanks a lot, Pablo. Let me share the screen again.
Okay.
Okay, so let me continue from where I left previously. I would like to thank a lot to Pablo Quesada for the kind words and the acknowledgements. So I'm going to explain how are we integrating a remote sensing 16-bit floating point algorithm with Cloud 5. Right now, the builds are triggered automatically using GitHub webhooks. So if someone goes on GitHub and creates a pull request, a build is triggered and you can see the console output. The second method is the manual builds. We have set up manual builds for debugging. So in case if someone needs to use multiple platforms for running the builds, let's say first we were running Vision 5.2 and then we want to run it on Vision 5.1. So that means we are running it manually. So for that purpose, I have set up manual builds. So anyone can go to the platform and run the builds and check the results. And the platforms which we are using to run the builds right now is such that we have compiled it on x86 instance and executed on QEMU user mode. After that, we have also compiled it on Vision 5.2 and executed on Vision 5.2. And lastly, we have compiled it on ARM instance and executed on an ARM compute instance. So here you can see how the pipeline looks like. On the first picture, you can see the stages and the result of the stages of the pipeline. And on the second picture, you can see how the result of a successful pipeline will look on the pull request. And lastly, I'm going to explain what are the partners of Cloud 5 and what are the users. So the first user is going, which I have not mentioned, is the Pablo, who is also the guest of the presentation today. And after that, we are also the RISC-V lab members, and we are world's first certified RISC-V lab member for 2024, or the RISC-V lab partner. And after that, we have llama.cpp, which is an AI LLM from Meta. We have ported it to RISC-V vector extension, and we are currently running free CI for testing RISC-V related changes of llama.cpp on our platform. And lastly, we have PLCT Labs. PLCT Labs is running CI for Node.js, LLVM, and GCC so that these programs can be ported to RISC-V architecture. In the user support, I'm going to explain to you that we provide 24/7 interactive technical support around the world for users, and this subjects to the RISC-V lab service level agreement requirements and other Cloud 5 policies. And we also have all the links to documentation, developer guides, and videos on our website. So you can go and visit our website in case you need to read our documentation or view the videos. And then we have selective support for open source communities. That means we provide free compute instance to the members of the open source community who are also the members of RISC-V International. And this is also subject to the RISC-V Lab service level agreement, so you can go and read it if you're included in this or not. And if you need to check whether or not your use case is included in the services that we provide, please refer to our services page for more details, so you can see whether or not your service can be catered by Cloud 5. So that was all about the presentations. Now you will be able to post questions in the comments, or you can directly contact us on the cloud-v@10xengineers.ai. And if you need to apply for the access, you can always go to our website, cloud-v.co, and apply for access there. So that was all for the webinar. I hope you have a very nice day.